Hi guys! Before we continue to this video, let me first introduce myself to you. I am Ninyo Mark Uy from BSc at 2A, and today we are going to make a tutorial video on Mechanics of Deformable Bodies. Our lesson for today is strain. First, let us define what is strain. In general terms, strain is a geometric quantity that measures the deformation of a body. There are two types of strain: normal strain, which characterizes dimensional changes, and the other one is the shear strain, which describes distortion or changes in angles. Strain describes the geometry of deformation. The normal strain is defined as the elongation per unit length, and therefore the normal strain in the bar in the axial direction, also known as the axial strain, is this. As seen in the figure, the stress-strain diagram is a straight line from the region O to a point called the proportional limit. This plot is a manifestation of Hooke's law. Stress is proportional to strain, that is this, where the big letter E is a material property known as the modulus of elasticity, or Young's modulus. Because the bar deforms uniformly, the formula for the axial strain is substituted into the Hooke's law. Therefore, the elongation of the bar is this. There are many subtopics on our main topic for today, the strain. There are actually loaded bars, there are statically indeterminate problems, but our focus for this tutorial video is the deformation caused by thermal strain. What is thermal strain? Basically, the thermal strain is a strain developed if an object is either heated or cooled. An increase in temperature results in expansion, whereas a temperature decrease produces contraction. Here is the formula for the thermal strain, where the constant alpha is a material property known as the coefficient of thermal expansion, and delta T is the temperature change. If the temperature change is uniform throughout the body, the thermal strain is also uniform. Consequently, the change in any dimension of the body is given by this one. Now let us solve some problem. A rigid horizontal bar of negligible mass is connected to two rods as shown in figure 275. If the system is initially stress-free, calculate the temperature change that will cause a tensile stress of 90 MPa in the brass rod. Assume that both rods are subjected to change in temperature. First, we will make an FBD out of this figure so that it will be easier for us to understand. Here is now our FBD. We have Rx, Ry, and force from the copper rod and the brass rod. Now we are going to solve for the tensile stress of the copper rod. We will be doing it by using moment of forces. We have summation of moment from VR is equals to 0 counterclockwise positive. We have force bronze with its moment arm 5 minus force copper with its moment arm 3 is equals to 0. We all know that stress is equals to P over A. P is equals to stress times A. We will be doing it by substituting the given. We will be substituting P by stress times A. And now we are gonna substitute the given values for us to acquire the tensile stress of the copper. By substituting it and equating it, we will gonna come up with the tensile stress for the copper is equals to 120 MPa. We are gonna be doing the deformation diagram of this figure, which is caused by the following strain. In the copper rod, we have its thermal strain minus its strain, and in the brass rod we have its strain minus its thermal strain. So looking back at the given, now we are gonna solve for the strains in each of the rods. So we have the formula for the strain is equals to tensile stress times length over the elongation. So the bras strain or the strain in bras rod, we are gonna be substituting those values that we have looked up the other slide. So by solving it, we are gonna come up with 1.8 millimeters. So that will be the strain on the brass rod. And now we are gonna compute for the strain in the copper rod. So again, we're gonna substitute those values again from the given, and we will be coming up with 3 millimeters of strain. So we are gonna solve this problem, or we are gonna solve for the change in temperature by using ratio and proportion. So the total strain in the copper rod and the total strain in the brass rod is proportional to each other because they deform as one. So the total strain in the copper rod with its distance from the hinge is 3 meters, which is proportional to the total strain of the brass rod with its distance from the hinge, which is 5 meters. Now, we are gonna eliminate these decimals. So we will be multiplying both sides by 15 because it is our LCD or the lowest common denominator, and distribute. So now we'll head on to our next step. So we will gonna be substituting these values to our equation. So we're gonna be substituting this formula to our equation. So we have 5 as the formula of the thermal strain minus 5 multiplied by the strain of the copper, which we solved earlier, which is 3 millimeters, is equals to 3 multiplied by the strain of the brass, which we also solved earlier, which is 1.8 millimeters, minus 3 times the thermal strain of the brass. So we will be using millimeter as our metric unit for this problem. We're gonna convert this alphas into millimeter because it is in micrometer. And now we have already set our given, and it is ready to be substituted into the equation. So all we're gonna do is to substitute this given into the equation. Oh, I almost forgot that our length is in meters, so we're gonna convert it into millimeters. Same as in the brass. So now that we have substituted all the values from the given, and we have left with one unknown only, which is the change in temperature. So we are gonna be simplifying this equation so that we will get the change in temperature. So now that we have come up into this equation, so we are gonna be dividing both sides by 0.3642 in order to get the change in temperature of this problem. So we are gonna solve this 20.4 over 0.3642. So we will get 56.01 degrees Celsius. And that is our change in temperature if the tensile stress of the brass is 90 MPa. So that's it. I hope you have learned something. I hope you have gathered something in this tutorial video, and it will also be a great help in our step-by-step civil engineering journey. So I think that's all. Thank you for watching. Adios.